A finite continued fraction is a fraction form looks like this. So it's the numerator of each the parts of fraction form is 1. And the denominator is a combination of a number plus a quotient form. Right? And it says finite means it's ending at certain moment. And at this moment, those i's like a0, a1, a2 up to all these steps, it's just any positive real numbers. Okay, so in some cases, this is very useful to define some number. Especially we talk about this one in several chapters before, like it's irrational numbers, and there are many different ways to define it. And one of them is like this type of style, the continued fraction step. So we want to just discuss about some parts of it. Okay? And because of the nature of the forms, it requires a lot of space if you want to keep this way. So instead of this one, we just invent kind of new notation like A0 semicolon and A1 comma A2 comma up to AN, which means you can translate this one like this one, right? So this is nice symbol or notation for this continued fraction. And the meaning of the, the simple, we just say it's a simple because the numerator is just 1. Okay? And the partial denominator parts of it is just integers. Okay? So we call that is simple. So which means all these A0, AI, A1, A2 is integers. Okay? So for any finite simple continued fraction, has a rational number because eventually it's end, right? If it's a finite, then it must end. Then you can calculate back to get this kind of rational number eventually. So let's say 5 semicolon 412 is 5412, right? And all the numerator is 1. And from here, this is 3 halves, right? Then 1 over 3 half means 2/3. So 4 plus 2/3, and that one is 12 over 3 plus 2 over 3, so 14 over 3, so 1 over 14 over 3. So it's a reciprocal of 14 over 3, which is 3/14. So 5 plus 3/14 becomes like that, right? So eventually, just any finite simple continued fraction is actually a rational number. That's clear, right? So when you start from any rational number, like a P over Q style, then it can be written to that finite, simple, continued fraction forms. So how can you do that? Actually, we need to take the division, right? And the quotient is 1, and for leftover, we just do certain procedures. So eventually, when you got this much, that notation, that finite simple continued fraction form looks like this, or another notation for that is 1, 3, 5 is enough. Of course, 1 semicolon and 3 comma, 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 like that, right? But it can be written like this way, because at the end, we can always change this one to, if it should be integer like that, then if it's n, then n minus 1 plus n, right, style. And instead of 1, we can put 1 over 1. So this portion changed to like that. Then for same rational number, p over q, can be written in these two different formats, right? The first one is 1 semicolon 3 comma 5. Then another method is 1 semicolon 3, and kind of looks like we separate this 5 to 4 and 1, right? It's always ending by 1, okay? But just the same numbers, right? Just a little bit different notations. So the question is, in the first place, how can you get those fraction forms, right? So let me explain that one here. First of all, the first part is simple. We just take the division, okay, 21 divided by 16, then quotient is 1, and 16, remainder is 5. Then we just get like a 21 over 16 is 1 plus 5 over 16, right? Then what was the rule for this continued fraction form? We want to make 1 at the numerator. So if it's 5, yeah, then we cannot take it. Then that is same as 1 plus, take the reciprocal of it. So 1 over 16 over 5. It's the same number, right? But now we got 1. So in here, definitely we can get some integer quotient because previously it was less than 1, which means this number is greater than 1, right? So take the division again, 16 and 5. Then it's 3, 15, and the remainder is 1. So just to pay attention for that part only, then quotient is 3 and remainder is 1, divisor is 5. That's how we got exactly over here. So from here we know it's 1, 3, 5. So we can write down 1 semicolon 3, 5, or we can go further one more step like that. But as you can see here, when you look at, we did this one before, like when we do the extended Euclidean algorithm or just Euclidean algorithm. In the beginning, the 16 was divisor, right? To divide that. But in the next step, 16 becomes the dividend, okay? And the remainder 5 becomes divisor, right? Okay, so we already did this stuff before. So exactly same style here. So let's just do the next example, applying this one. So changing this P over Q style into a finite simple continued fraction. Because it's a rational number, it should be stopped at certain moment, okay? So first thing is, let's divide 172 by 51. The quotient is 3. So 153, remainder is 19, which means that 172 over 51 is quotient plus remainder over divisor, or it's 1 over 15 over 19. And that tells us what we are supposed to do, right? 51 becomes dividend and remainder 19 becomes divisor. Then right now by 2, it's 38 over remainder is 13. So by that we have 1 over, that is 2 plus, now you can say, yeah, remainder is 13 and divisor was 19. You can write down that one. But we know this should be 3 plus 1 over 2 plus 1 over 19 over 13, right? So 19 over 13 is 1, 13, remainder is 6, right? So that is 3 plus 1 over 2 plus 1 over, and quotient is 1, remainder is 6 by 13. And you know what we are supposed to do, right? It's the 13 divided by 6, right? So 2, 12, remainder is 1. Okay, I think that's the last step here. Then it's 2 plus 1 over 1 plus, and that, remember, I didn't write down this format, right? But it's 1 over 13, 6, right? So 1 over, and 13 over 6 is remainder, the quotient is 2, and remainder is 1, 6, right? So it becomes 1. Then we know it's the time we can stop here, right? So you can write down this one. Oh, this is the answer, right? This is really the finite simple continued fraction form, but in our notation, simpler one is 3 semicolon 2 comma 1 comma 2 comma 6. Okay. Now, for any finite continued fraction form like this, we can actually make the finite sequence whose limit becomes that number itself. So using this A0, A1, A2 collection of it, okay, we can make some kind of small finite number of sequence. Okay. And how can you do that? We just simply cutting out each moment like this, like that. So you know what I mean, right? So the first one is just A0. We don't need to put the bracket around it, but let me just keep that. The next one is A0 semicolon A1. Second one is A0 semicolon A1 comma A2. So if you keep doing this way, the last one is the one we have, right? Up to AN. So when you calculate each of these values, they are not exactly same as the one we are looking for, right? But when you look at these numbers as a sequence, then these numbers are kind of approaching to this number, right? One by one. So let's just define some rules and terminologies for doing this way. So first of all, we can just get to the kth partial, the cutting off that up to the kth partial denominator to a sub k style. So we call that is kth convergence of the given continued fraction, and it's called c sub k. So convergent, kth convergent. So I already mentioned that C, capital C sub k is starting from A0 up to finish at AK at certain moment. So this K could go up to just N, right? That's the last one. And of course, the starting value for K is actually is 0, right? Because at this time, the reason put 1 is we are looking for the denominator or something like that, right? So A0 is not denominator, but eventually K could be 0 even, right? So C sub 0 is simply A0. Okay? So that's kind of initial value for the sequence, and you can just building up this finite sequence for that. So let's just pay attention for that. If our given rational number is P over Q, which is like that 2322 over 631, then after you calculate it, we got that finite simple continued fraction forms like this one. Then what is C2? That is k equals 0, k equals 1, k equals 2, right? So we are looking for this much. So C sub 2 is the same as that one. Then by our definition, it can be written by in this one, right? This is original format. Then you can calculate it. This is 3/2, so it's 2/3, right? So 3 plus 2/3 becomes 11/3. So C sub 2 is 11/3. Of course, it's not same as that one, but this C sub k is approaching to there. So when you got C sub, let's say 3, 4, 5, right? C sub 5 is exactly same as that one. So let's find the first conversion of that previous number. So it's just simple calculation right now. C sub 4 is just 3 semicolon 1 comma 2 comma 8 comma 12. One just before that actual number. Okay. Then it's 3 plus 1 over 1 plus 1 over 2 plus 1 over 8 plus 1 over 12. Then just do one by one. That is 97 over 12. Please check. So this is 3 plus 1 over 1 plus 1 over 2 plus 1297, right? And that is 1 over, and 2 is same as 180, but 194 over 97, right? And plus 12 over 97 as the denominator. So it's all together, it's 3 plus 1 over 1 plus, when you're adding them, it's 206 over 97, right, as a denominator. So it becomes 97 over 206. So that is 1 over, and 206 plus 97 is 303, right? So 303 over 206. Then that is 206 over 303. So altogether is 909 plus 206 over 303. So it's 1115 over 303, right? So that should be the answer. Okay? Now, I assuming like we have some kind of fear to ask, like calculating such a ck, right? For long stuff, right? Like a c sub 10. Wow, then we have to really calculate starting from the bottom, right? And going up all the ways too much, right? It's just simple arithmetic, but there's too many arithmetics involved for that calculation. But you can find some kind of pattern there. So, always like to take the reciprocal of it or like that, right? So, after we figure out certain things from that finite continuous fraction form, we could define the small p's and q's like this. Starting with p sub negative 2 is 0, p sub negative 1 is 1. And p sub k is just like that, right? A, k's are given like that. And this p sub k minus 1, k minus 2 is previously defined, right? And k is for any 0 through n. And q sub negative 2, q sub negative 1 is 1 and 0. And q sub k is defined like this. So when you look at this, and when you write down that, 0, 1, 1, 0. So familiar, right? We had this one in extended Euclidean algorithm before, right? So this whole concept is very similar, right? Because the divisor becomes dividend and remainder becomes divisor in extended Euclidean algorithm. Same thing happens. We just same method here, right? So that's why we need those kind of setting for easier calculation, right? Then the conclusion for that is to calculate C sub k, all we need is just pk and qk. You can calculate like this, right? So just imagine this one is much easier than calculating those fraction forms, right? Than many times. So this is nice kind of inputs, right? The table method you could use, right? Please remember that. So you need these kind of 5 columns, and the first one is the index part, right? The k, and k start from negative 2, right? And all the way to whatever the n is given. And a sub k, it should be given when they give you the question like that, right? Or you might need to find by yourself, but just write down. First two, for k equals negative 2 or negative 1, we don't need it, we don't have it, right? AK start from A0, right? So if it's that, then it's 3, 1 like that. So just write down that. And PK, QKs for k equals negative 2 and negative 1 is already fixed, right? Like that. So 0, 1, 1, 0. And C sub k is reasonable when k equals 0, right? So nothing in there, right? Okay, so let's just calculate this one. Then just imagine in the previous page, we solved this one after we convert that to 3 plus 1 over 1 plus 1 over 2 plus 1 over 8 plus 1 over 12 plus 1 over 2, right? And that is 25 over 2, so it's 2 over 25. Then 8 plus 2 over 25 is 25. You know what I mean, right? So you have to go all the way like that. But in this table method, all we need is those two formulas, right? So pk is, okay, pk means, right now is p0, right? So p0 means a0, so use this one, times pk minus 1, just one before, right? So we need to multiply these two. Okay, we need to multiply these two and adding p sub k minus 1. Okay, like that. So it's going to be 3 times 1 plus 0, right? So all you need is those three cells, right? So next one is we need to multiply these two values and adding 1 above. So 1 times 3 plus 1, which is 4. And 2 times 4 plus 3 is 11, right? And 8 times 11 plus 4, so 88, so 92. And 12 times 92 plus 11, okay? So I'm lazy, so let me just calculate here. So 12 times 92 is 1104, okay? So adding 11 means 11, 15, right? And the last one is 2 times 11, 15 plus 92. So it's 2 to 30, but 92 means 30, 27. Okay. Please let me know if I'm wrong. Right? So this 1115 times 2 plus 92. Okay. Okay, so it's just the 2, right? 2322. Okay. And let's just do the same thing. For q sub k, we multiply ak times 1 above plus 1 above, right? So the rules are just the same, right? This pk or sub k, doesn't matter, same rule. Just use different column values. So 3 times 0 plus 1 is 1, and 1 times 1 plus 1 equals 2. 2 times 2 plus 1 equals 5. 8 times 5 plus 2 equals 42. 12 times 42 plus 5. So 12 times 42 plus 5 is 509. And the last one is 2 times 509 plus 42. So 1018 and plus 42. So 1050 or 60, right? Like that. So please let me know if I made any mistake here. Okay. Okay. I think it's right, right? Okay. So then C sub k. So this table is not only giving us that certain k, right? It's a list of whole C sub k, right? So the first one is pk over qk, right? Next one is 4 over 2, which is 4, right? Am I right? Oh, okay. I made a mistake. Sorry. Here. Sorry. It's 1 above, right? So it's not 1. When you multiply 1 and 1, then I have to add the one previous one. So it's still 1. Okay? And here, 2 times 1 plus 1. So now we got 3. And 8 times 3 plus 1. So it's 25. And 12 times 25 plus 3 right now. So it becomes just 303. And 2 times 303 plus 25. It's just 631 or something like that. Okay. So this one is P0 over Q0 is 3. And P1 over Q1 is 4. Right? And 11 over 3, 90, 2 over 25, 11, 15 over 303, and 23, 22 over 631, right? Whatever. So those are the C sub like 0, C sub 1, C sub 2, C sub 3, C sub 4, C sub 5. So as you can see here, just maybe we just spend exact same time, but we got all of them, not only just one single stuff, right? So this much, this table method is kind of effective to finding all these convergent values. Now then, as I mentioned before, there are uses of these infinite fraction forms, right? So let's just thinking about infinite continuous fraction forms. So it's not finished. It just keep doing, right? This dot 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 means it keep going this way. So the notation for that simpler one looks like this way, right? With dot 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 at the end. Then how can you calculate this if it goes forever? Right? So we cannot use this kind of table method anymore because it just keeps doing it, right? So because of that, we need to find kind of general rules of C sub k and take the limits of it, right? This C sub k goes forever. Then where does it goes, right? When k goes to infinity, right? Then that should be the result of this, right? Okay, so that's the main concept here. So let's see some example how we're gonna calculate those. But key point here is this number is a real number, right? Because it's just fraction forms. You keep going. But do you remember when you talk about the real number set in the number system? The real number set is complete, which means if you have a sequence, right? Then the limits of it must exist, right? If it's a rational number, there is many holes, right? So even that sequence might goes to that point, which is not rational number, then in rational number set, it's not complete. So we are not gonna get the limit of it. But if it's a real number set, then when you take the sequence like this, of course, if it's oscillating, then there is no limit. But if it's just going one direction, and if the limit exists, then that limit must really exist as a real number. Okay? So this continuous fraction form, if it has a limit value, then that limit value must be a real number. Okay? So let's just try to find that. So let's say the limit exists, right? So that should be like this, right? And because it's just repeat of 1 forever, so better notation is just like this, right? 1 bar. Bar means repeat parts of it. Then it must be 1 plus 1 over 1 plus 1 over 1 plus 1 over dot 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 like that. Then do you remember when we covered the fractal geometry? What is the definition of fractal? They're like Spansky triangles. When you look at the portion of it, that is exactly same as the entire shape, right? So in this infinite fraction forms, when you look at just this portion only, this looks like exactly same as the original fraction forms, right? That's the power of infinity, right? The, it's not exactly matching, but the concept is the proper subset, the proper part of it is exactly same as its original set. Same thing, right? This parts of the entire equation is same as the entire one, right? And we said that x equals this entire one, then maybe this, not maybe, this portion should be also equals x, right? So we can change that one to 1 plus 1 over x. So x equals 1 plus 1 over x. let me multiply x on both sides to remove this x. So it's x squared. And of course, at this moment, the assumption is x is not 0 because this fraction form looks like this, right? So definitely it's greater than 1, right? So 1 plus some positive number. So this number is greater than 1. Okay? So it's not 0. So we can multiply x on both sides and we still keep this equality. For that, then it's going to look like this way, right? So it's just a simple quadratic equation. Okay, it's a little bit difficult to get the factorization form. So let's apply quadratic formula. So negative b plus minus square root of b squared minus 4ac over 2a. Right? So it's 1 plus minus square root of 1 plus 4, which is 5 over 2, right? Now, square root of 5 is about 2 point something, right? So 1 minus square root of 5 is 1 minus 2 point something. So it's negative 1 point something, right? It's less than 0. So it's negative number. So this x suggests 1 plus square root of 5 over 2 and 1 minus square root of 5 2. And 1 minus square root of 5 over 2 is negative, right? But we already knew that x must be positive, right? And even greater than 1, right? So we cannot accept this one. So even we got two different answers for x, we only got, because of that reason, x must be just 1 plus square root 5 over 2. And that should be the answer. Okay, so that infinite fraction form 1, 1, 1, 1, dot, 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 is actually 1 plus square root 5 over 2. So now we see the difference between the finite fraction form and infinite fraction form. Finite fraction form is definitely rational number, but this infinite fraction form is, in this case, is irrational number. Okay? But the question is, then, any infinite fraction form is irrational? Okay, that could be a good, nice question. Please figure it out by yourself. But if we choose irrational number, then there is a unique representation as an infinite continued fraction. Be careful. This one says any irrational number can be written by infinite continued fraction form like this. Okay? Uniquely, there's only one single format like that. But this one doesn't say anything at all, like any infinite fraction form is for an irrational number. We are not so sure about that yet. We haven't covered that. So the next question is, okay, then how about square root of 3? We know that is irrational number, but can you write down that one as infinite continued fraction form, right? Now, before solve this one, let me ask you one question. Do you know how big, let's say, square root of 19 is, roughly? So, at least the integer part of it. How do you know, right? How about square root of 115? Okay. What is the integer part of it if you change that onto decimal? All you need is just two complete squared of any integer around this. So before that, I think 16 is the kind of closest one, which is smaller than that and complete square form. And after that, it's 25, right? Then square root of 16 is 4, and square root of 25 is 5. So we know square root of 19 is between 4 and 5, right? So integer part of that is 4 point something something, right? Same thing, like 115. What is the complete square form, which is the largest one and less than 115? 10 square is 100, right? And 11 square is 121. So I think it should be 120. 121, right? Then it's 10 and 11. So square root of 115 is 10 point something something. Okay. So this is how we figure out the integer part of any square root forms. Okay? And actually, we apply the same rule for like a cubic root, right? Cube root. So 115. Then what is the smallest integer, which is cubic of some integer, right? So uh, 5 times 5 times 5 is 125, I think, right? So it's less than that. So 444. So 64, right? And after that is 125. So it's going to be 4 and 5. So cube root of 115 is 4 point something, right? Right for me? So like this way. So when you try to change this one to as an infinite simple continued fraction forms, we have to figure out what is the integer part of it, right? So we know, you might remember like square root of 3 is 1.7 something, but if you remember and if you want to make sure that, you can just simply show that square root of 3 is surrounded by square root of 1 and square root of 4, which is 1 and 2, right? So we know square root of 3 is 1 point something, right? And that is same as 1 plus 1 over certain things, right? Which you don't know, right? But that is enough to claim C sub 0, okay, that A0 is 1, okay, for square root of 3. Okay. So not directly equal because this one is square root of 3, but we can say just 1 is C sub 0. Okay. Then the next one is important. We are looking for the infinite simple continued fraction form of square root of 3, and we found out the integer part of square root of 3 is 1. Then we can say 1 plus, so we just kind of bring out the integer part from square root of 3 and subtract 1. And that is exactly same as square root of 3, right? We don't touch anything, but we just change the form of it. Then this one can be changed to 1 plus, and this is actually that part, right? Then we want to write down this one as 1 over something style, but this is not fraction form, so how can you change it? Yeah, take the reciprocal of reciprocal. So it's 1 over square root 3 minus 1. Like 2 equals 1 over 1 half, right? Okay, that's the format. So we just get this much, right? Then to change this form, the denominator, we have radical forms it. Then you know how to get the rationalizer of it, multiplying the conjugate of it, right? So like 1 over square root of 3 minus 1, we multiply square root of 3 plus 1, square root of 3 plus 1. Okay, at numerator, denominator. The numerator is just like that. Denominator is a minus b times a plus b, which means a squared minus b squared, right? So together we have 3 minus 1 is 2, right? Okay, so this one changed to 1 plus 1 over square root of 3 plus 1 over 2, right? And now we need that technique again. We don't know how big this number is, but we need to find out what is the integer part of it. So we want to change this one to 1 plus 1 over some integer plus 1 over something like that, right? So we need that integer parts of it. So to calculate it, right now, let me just assume we know that what square root of 3 is. So square root of 3 plus 1 is 1.7 plus 1 is 2.7, right? So that is about 2.7. So divide by 2 means divide by 2 is 1 point something. And that's enough, right? So it's going to be between 1 and 2 again, right? So now we just apply same rule like we did over here. Is 1 plus 1 over, instead of that, let's just bring out that 1, right? First. Then inside, we want to subtract 1, that integer part, right? So nothing changed. We can keep this equality. But now we have from here like a 1 half minus 1, which means minus 1 half, right? So square root 3 minus 1 over 2. Okay. So clear thing here is this one is greater than 1. It has some constant term. I mean, not constant, it's the integer part, right? But this one is only that decimal part, right? It's between 0 and 1, right? So this portion can be written by 1 over something style, right? So we want to take the reciprocal of it one more time. So it's 1 plus 1 over 1 plus, when you take the reciprocal, it's just simply 2 over square root 3. But we want to really count that, right? So instead of doing that, we want to multiply or check like a square root 3 minus 1 over 2 and square root 3 plus 1 over square root 3 plus 1, right? Multiply and conjugate. So it's 3 minus 1 over 2 times square root 3 plus 1. Then this is 2 over 2 square root 3 plus 1. So we have nice cancellation. We have 1 over square root 3 plus 1 only, right? So we can get 1 over square root 3 plus 1 here because of this. Then from here, we know it's 1 comma 1 semicolon 1, right? We got that much, and that should be C sub 1. Okay? Then let's go further. We just got 1 plus 1 over 1 plus 1 over square root 3 plus 1. Okay? So we need to check certain things, but let me write down over here. Square root 3 plus 1 is close to 1.7 plus 1. So which is 2.7 something. So it's between 2 and 7, right? That number. So let me just do right away because we know how to do that. Square root 3 plus 1 has 2 as an integer part. So bring out 2 first. Then the remaining one is square root of 3 plus 1 minus 2, right? So let me just put negative 1 again. So do we have to keep doing this way? No. Look at here. At this moment, we have square root of 3 minus 1, which is here. So we know that result must be like this, right? Okay, so eventually we are going to get from here, right? We just got this much. So that can be changed to, can you see that? How we got it, right? Like that. So this one from here, we got 1 semicolon 1 comma 2. That's for C2, right? And after that, it's going to repeat like 1 and 2, 1 and 2, 1 and 2, right? So finally, like this this sequence, right? Looks like next one, C3 must be 1 semicolon 1 2 1, right? And C4 is 1 semicolon 1 2 1 2, right? And keep doing it. And the limits of this is square root of 3, right? Okay, so square root of 3 is the limits of this ck, and it should look like 1 semicolon 1 comma 2 1 comma 2. So this is the answer, or you can write 1 semicolon 1 comma 2 bar. Okay, so that's the result of square root of 3. And the following homework question is just for calculation like that. Okay, so I wish you have fun. And that's the end of chapter 26.